Good afternoon. Welcome at this Tech at Lunch webinar on optical detection in industrial applications from imaging to spectroscopy. I am Liens Meesters. I'm a postdoctoral researcher at the Flanders Make and VUB Core laboratories, the BPhot Brussels Photonics Research Group. Before we start, just a few practical aspects. All cameras and microphones are muted by default. However, I would strongly encourage you to ask all your questions in the Q&A chat box, and I will address them at the end of the presentation. This session will be recorded, and the recording will be shared later on with you. It is not allowed to record the session yourself. Okay, so to our optical detection techniques. So basically in this presentation, I want to highlight the industrial applications of optical photonics sensors, both covering camera-based technologies as spectroscopy. If you think of photonics, light-based technology, then you might immediately think of cameras, you might think of fiber-to-the-home applications, but did you ever thought of photonics technologies as a suitable technique to measure the constituents, the composition of your glass of water? A lot of people first immediately think of chemical analysis to determine the composition of this water. However, when we study the interaction of light with this water, we can really obtain valuable information about the different constituents that are present. Now, how does this work? If we illuminate a sample under test, like for example, this rectangular sample, if we illuminate this with an incident beam of light, then part of the light will be reflected, part of the light be absorbed, and part of the light be transmitted. Which interactions there occur is actually dependent on the chemical composition of this sample. Now, this, of course, is a really vague simplification, because in fact, much more interactions will occur. In fact, if you study your sample, we can differentiate the reflection in specular reflection and in diffuse reflection, dependent also on the surface roughnesses. Also, the light can be absorbed, but this absorbed light can also induce new photons, new light photons, as fluorescent light emission. Transmitted light can just transmit through, but actually there can also be internal scattering. When we study the spectrum, the light interaction for all of these interactions, we basically can measure the spectrum, which is a light intensity as function of the wavelength. And this spectrum contains information about the chemical structure of our sample under test. More specifically, when we illuminate our sample, then all the different wavelengths will interact with the molecular structure of our sample. You might recall that all matter comprises of one molecular structure, and this molecular structure actually comprises atoms, and they have a nucleus and an electron around them. Our incident photons, or incident light particles, are going to interact with this electronic structure, and when the energy of our light wave matches the one with the electronic structure, we can basically excite these electrons. An easy example, if we illuminate a red apple using white light, then basically all the light will be absorbed, all the colors, except for the red one, which will be reflected. And that's also the reason why we see this red apple as red. Now, the nice thing about this is that dependent on the wavelength which we use, we can play with the levels that we are going to excite. Like for ultraviolet, visible, infrared light, we can play if we excite the electron transitions or if we play on the molecular vibration level. So basically, dependent on the wavelength with which we illuminate our sample, we will gain different information about our sample under test. Now, this principle might sound really useful and has a large potential, but of course, to be able to use it, the principle on itself is not enough, and we need to go through a whole supply chain, starting from a broadband spectroscopic study to identify the illumination detection wavelengths. Of course, we need to combine this with advanced data processing, also including machine learning, to be able to really come up with an optimized optical detection method. having an optimized illumination and an optimized detection. And then after we identified these illumination conditions, we take into account natural variation and we can start generating a prototype. Now, to make this a little bit more concrete, also with a view on industrial applications, I will go through 3 different case studies. First one with press buttons of Van Hol, which is basically a color evaluation study, one with sorting machines, and then one on a camera-based system for turf grass monitoring. So let's start with the first one. You might have seen these press buttons already in public transport. They are quite widely available and they are available in quite some different types. You can see here, some of them have a black background, some of them yellow, and also there is some variation in the color of the press button. Now, dependent on your favorite color, you might have a preference for which button you like the most. But actually, these buttons, we want them to stand out. So we want to maximize the color contrast between the button and the housing. Now, how can we measure that? To determine which color combination is the best and to determine which color contrast is the best visible, we started by measuring the reflection spectrum. We used therefore 2 different measurement configurations, one on the left where we measure broadband all reflected light of the button and the housing. So basically here we use an integrating sphere on which a sample is positioned. We illuminate the sample, the press button, with broadband light, so visible near infrared light, and we collect all reflected light by the integrating sphere and send it to the spectrum analyzer. The second setup, which we considered, is also measuring the reflected light, but only the diffuse reflected light. So basically, here we have a sphere. It collects all reflected light except for the specular component, which is here going out in a light trap. Using these measurement configurations, we thus clearly know what portion of the light is diffuse reflected, which part is specular reflected, and we also know what is the total amount of reflected light via an absolute measurement. Using these press buttons and separating them in terms of color, we get these raw spectral data. You see, dependent on the color of the button, the reflectance spectrum is altered. Of course, the blue button is reflecting main part in the blue spectrum of the light. The red button is reflecting most part in the red part of the spectrum. Now, these spectra, of course, are already useful, but basically, to be able to know which color combinations are the best for our eye, for our human perception, we need to take into account the sensitivity of the human eye. So basically, these spectra were post-processed using our human eye sensitivity curves and also calculating the color coordinates. After this post-processing, we could then come up with a visual contrast calculation where we see, dependent on the value of the visual contrast, we get better and worse combinations for the press buttons. Second application of optical spectroscopy and optical sensors are optical food sorting machines. And basically here we pursue the development of a generic food sorting machine, a food sorting layout for walnut sorting. To date, these food sorting machines are typically application specific and are really optimized towards the good products and the defects that they want to identify. While in our research project, we wanted to come up with a general approach for walnuts, where we are able to sort based on product quality and on foreign objects using a single unit. Now, to do that and to understand our approach here, let's first take a look to the scanning-based platform. So using these food sorting machines, basically they combine different illumination lasers here that are guided to the sample via polygon mirror. The laser interacts with the walnuts and all reflected, fluorescent, scattered light signals are again collected by the polygon mirror and guided towards the detectors. Using this type of configuration, we pursued the identification of the most optimal laser lines and the most optimal detection unit, while also focusing on the post-processing using machine learning. Now, as I said before, we don't only want to identify good walnuts, we want to differentiate good walnuts from a wide range of different defects that can be there based on the quality of the walnuts. So you see here the walnut shells, but also some darker walnuts, some moldy walnuts that are present, which we don't want, of course, in our good food products batch. And in addition to this, we also wanted to detect foreign objects like small pieces of glass, small pieces of stones, some other grains that might end up in the product flow. So by focusing on this multi-defect sensing algorithm that we wanted to develop, we needed to combine different technologies. So basically, to be able to sense as much as possible defects as possible, we focused on the combination of reflection spectroscopy and fluorescence spectroscopy together with the machine learning processing. Now, first, let it take step by step, and let us take a view on the reflection spectroscopy measurements. Because, of course, before we can integrate some lasers into a food sorting machine, we, of course, need to identify which lasers are useful and which processing is required. So first, reflection spectroscopy. Using a similar setup as before, we measured the visible near-infrared reflection spectrum of all our samples. So basically here as well, we illuminate with a broadband light source using an integrating sphere, and then we have our detection spectrum analyzers. So here our sample is positioned on top of the integrating sphere, and as before, we are collecting all reflected light. Considering the spectra, you can see the spectrum of the good walnuts in green in both graphs. They are splitted. In the top one, you can see the product quality-based evaluation, and here you can see the evaluation for the foreign objects. In general, you cannot see that much separation, I would say, because all the spectra are very diverse. There is some small dip at 1200 nanometer, but basically, if you consider the natural variation at 1200 nanometer, you can see that actually it's all mixed. Pure from the spectra, visual inspection, there is nothing that you can derive. You see here the red lines are like the mean values, and then the blue box around it is a box plot graph with then the outliners here on the end and below. So you see basically, yeah, there is nothing much you can do with just a single wavelength, and based on just the pure spectra, they're all mixed. This indicates the need for more advanced processing and for the addition also of other technologies. So therefore, we wanted to combine our reflection spectroscopy with fluorescence spectroscopy. And for our fluorescence spectroscopic study, we studied the influence as well of the excitation wavelength. So basically, we used a tunable laser setup that you can see over here, where we are able to generate different excitation wavelengths such that we are able to study the influence on the excitation wavelengths on the fluorescence signal. Why do we want to study this? This is because we don't want to only optimize the fluorescence signal of the good walnuts, but we also wanted to reduce the background signals and to really have a full view on the influence of the excitation wavelength. For our study, we identified two particular interesting excitation wavelengths, which was 405 nanometer and 660 nanometer. Considering the fluorescence spectra achieved after excitation using 405 nanometer light, you can see the spectra over here. Basically, the spectra contain two peaks. First one, which is visible here, which is due to the proteins that are present. And then a second one between 650 and 700 nanometer because of chlorophyll presence. You see here with 405 nanometer excitation light, we get quite some large fluorescence signals. The healthy, the good walnuts are the green ones and are somewhere similar to the other ones. So not the most optimal excitation wavelength. If we go to 660 nanometer excitation wavelength, you see that we again get a fluorescence spectrum, similar similar one as the last part here of chlorophyll, but still now we get a larger contrast between our samples. Some samples are showing still high fluorescence, while other ones are showing a lower fluorescence signal. Now, also using just fluorescence spectroscopy, we are not able to obtain satisfying results. So what we did is we used a cascade data processing algorithm combining reflection and fluorescence spectroscopy. And this is visualized in this table. I will go step by step through this table to give you the main conclusions here so that you don't get lost. So first of all, we combined reflection spectroscopy and fluorescence spectroscopy into a cascade algorithm. And this table gives for all the samples the false classification rate, meaning the percentage of samples that were still wrongly classified. Given the good walnuts, you see that here 5.5% were classified wrongly as an unwanted product. Now, considering reflection spectroscopy and just combining reflection spectroscopy with extreme learning machine, we obtained following classification rates. So you see, for a lot of defects, it's actually working quite well, except for walnut shells. There we get half of the samples that are wrong classified, and also the shriveled walnuts are really not optimally classified. However, combining this reflection spectroscopy with fluorescence spectroscopy and support vector machines, we see that when we use these two in a cascade, we are able to improve the walnut shell sorting to a false classification rate of only 0.5%, which means that now all of the walnut shells are correctly, or almost all are correctly identified. For the shriveled walnuts, we reach a percentage of 8%, which is still a significant improvement if you compare it to the false classification rates of fluorescence and reflection individually, and which also is the most difficult product to differentiate from the good walnuts. So after all, this is a significant improvement to the state of the art and enables to have one single platform using 8 wavelengths, 6 for reflection, 2 of fluorescence, and detect all of these defects using one single configuration. Last example is for PhotonHub Europe, where basically we developed a multispectral, a 5-channel camera system for turfgrass monitoring. What was the objective? In this project, we wanted to develop a camera system that enables the sensing of the vegetation indices of turfgrass areas. So basically, we wanted to monitor the condition of the turfgrass, like the irrigation needs, the use of pesticides, to see if there was an infection or something on the turfgrass area. This can be for interest for football stadia, but also, for example, for golf yards and so on. In contrast to the current often used systems with drones that have a very narrow field of view, we pursued the development of a fixed system that can be mounted in the lighting poles that are present and thus needed to have a very, very wide field of view, so a very wide opening angle exceeding 150 degrees to be able to capture the whole field at once and thus to limit the number of required camera systems. So you see here our targeted camera system, where we of course also wanted to connect this camera system, this image processing, to some smart image evaluation that could immediately spot the areas where irrigation would be needed or where some pesticides would need to be applied. As such, to go to smart precision farming and reduce the need for the use of resources. So as said, we wanted to make our camera system comprising of 5 channels, where the spectral range of these channels is optimized towards the vegetation indices. So we first did a study here towards the vegetation indices of interest, where you see the typical NDVI index, which is frequently used, but also some other indices of interest that are combining different wavelength regions. So you see here we needed a near infrared channel. Here you see also 450 nanometer popping up, the red edge, and then also we wanted to include a thermal channel for water monitoring and health status sensing. So at the end, we came up with a layout of 5 channels, 1 thermal channel in combination with 4 visible near-infrared channels. Going to the visible channels, we optimized our filters such to match the vegetation indices. So basically, you see here an image of the 4 visible channels where we cemented a filter on top. And these filters were optimized, as you can see here, towards the different indices that we wanted to sense. So here you see also 1 channel that is covering the full visible wavelength band, but then you also see here popping up a band around 600 nanometer, 1 more towards the red and the near infrared. These 4 channels were combined with the thermal imaging channel into the layout of the 5-channel system. This layout and also the mounting and the correct distances actually between the lenses, the image sensors, so the mounting and alignment plates were fully made in-house in our Photonics Innovation Center. Afterwards, after the design of this camera, we characterized the camera also in-house by measuring the modulation transfer function. The modulation transfer function is actually a value of how well your camera is performing, how well he is imaging a certain frequency. So basically what we do there is we take an object with some frequency component present, we image it by our camera system, and we evaluate how good the contrast is still preserved at our image sensor, at our image that we obtain. And as such, we are able to measure this contrast as function of different frequency components, which is called the modulation transfer function. We did this measurement for a visible camera channel, where you see that we achieve 75 lines per millimeter for an MTF value of 0.5, which is actually a very nice image quality, as well as for the thermal camera, where we now reach 29 lines per millimeter for an MTF of 0.5. For the thermal camera, it's traditionally the case that the frequency component is always lower because also of the larger pixel sizes that are present. I give you a glimpse now on 3 particular application areas. Of course, the application domain of optical spectroscopy is much larger. Basically, it can be used on any food products. We can really do broadband studies to identify and to characterize the products, but also in addition to food, it can be useful to date and to investigate stained glasses. But also in more Industry 4.0 applications, like for example in laser cutting systems, we do spectroscopy studies to really evaluate the absorption characteristics of the different materials to also make sure the settings of the laser cutter are set at the most optimal performance. And with this, I would like to end my presentation with a small conclusion. I hope during this presentation, I was able to convince you that optical spectroscopy is a really valuable tool for the characterization and identification of products. It's a non-destructive technique, so we only use light to illuminate our sample. We study the interaction of the light with the sample under test, and based on the data processing that we achieve from that, we are able to extract the characteristics and the optical properties of our samples. We then use these characteristics in advanced data processing to differentiate between the products and to determine the composition of the products really accurately. If you look to the current ongoing trends, then we see the miniaturization of these optical sensing techniques into miniaturized compact handheld units. Also the multimodal sensing, like what I wanted to do with the food sorting machines, where we really go to a combination of optical sensing techniques for a combination of products. And of course, more and more we see the machine learning and AI processing popping up to extend the range of applications and to decrease the limit of detection. And with this, I would like to thank you for your attention, and I would like to give the floor to Sepper, who will be coordinating the Q&A.
Okay, thank you, Lien, for this clear explanation of spectroscopy. Well, we have 2 questions so far. So before I start asking them, I want to call out to everyone. If you still have questions, just use the Q&A chat box into the Teams interface, where you can type your questions, and we will be trying to answer them here. So the first question, for the stop button visual contrast, did you consider people with color vision deviation as well?
For now, not yet. I know that is an important issue, but for now we just based our evaluation on the CIE norms. Basically, the minimum color contrast that needs to be present is also regulated by CIE norms, where there are advisory limits present. So that was currently what we took as the norm into our study. But for sure, I fully agree that it's is interesting for future work to also take that into account.
Okay, thank you. The second question that we have is, did you have to develop new models, techniques to process the measured data, or could you use existing ML models? How do you approach this?
At the moment, we use existing machine learning models. So basically what we did is, for the reflection spectroscopy, we evaluated also different models, also neural networks and so on, to optimize our data processing. Also for fluorescence spectroscopy, there we used existing models to evaluate the fluorescence spectral data. But then our cascade method, where we combined the different techniques, this is basically code that we wrote ourselves. Also, the feature selection tool to select the most suitable wavelength is also code that we programmed in-house, because basically for the feature selection, we don't only use individual wavelengths like it's given here, but further optimization was also performed using ratios of wavelengths as the features, because then you immediately cancel out the offsets. So basically the foundation, we built on the foundation that is already there on the existing machine learning models, but for the data processing, we then combine them using our custom code, and also we make some custom code for the feature selection tools that we are using.
Okay, thank you. Next question, Lynn, do you have a spectral library for food inspection?
Excuse me, Sepa?
Do you have a spectral library for food inspection, is the question.
We have, of course, a wide range of data sets on all the food products that we investigated before, including maize, nuts, and so on. But this is our in-house tool. So we have a large database that we use in-house, but this is not publicly available.
Okay. There are no more questions at this moment. So it's just we are in fact 1 o'clock. So right within the time schedule that we have planned for this session. So we will wrap up this session. If you still have questions, you can still ask them in the Q&A. We will see them coming and try to answer you individually by email, for example. So don't hesitate to ask any more questions if you have. And I'll give back the floor to Lynn to close this session.
Thank you, Sepa. And I would also like to thank everyone for attending this Tech at Lunch webinar. And as Sepa already indicated, if you have any further questions or you want to have more information on one of the tackled case studies, certainly feel free to contact me via email or via Sepa. Thank you.